Okay. Good afternoon, everybody. Welcome to online classes on GATE in Transportation Engineering. And today it is eighth lecture. And in the last class, we are in design of pavements. Let us continue the same topic. Let us have a little bit more attention towards equivalent single wheel load. Already in the last class we have discussed this thoroughly, but let us see overall view of some of the different parts of the concepts. So equivalent single wheel load. Already it is discussed clearly. But here, this is the type of situation where tandem wheels are coming into picture. So these tandem wheels are very close together, so that the distribution of the stresses below the surface is because of both the wheel loads. And here we can divide it into three different parts as discussed earlier. The clear distance between the two wheels is small d. Center to center spacing between the two wheels is S. And if you draw the load distribution, stress distribution diagrams at an angle of 45 degrees, and these will intersect at one point. This will intersect at this particular point. This will intersect at this particular point. Till that depth, that means up to the depth of d/2, both the loads are acting independently. So equivalent single wheel load is nothing but only P. So up to the depth of d/2, equivalent single wheel load is P only. And when the depth is beyond 2s, at this level you can see this line is crossing the edge of the other one, and this distribution line is crossing the edge of the other one, so that below it complete overlapping takes place. When complete overlapping takes place, the equivalent single wheel load is 2P. And when there is no overlapping at all, in such a case ESWL is P. And in between these two to P1, that can be obtained by means of interpolation. So already discussed earlier, let us have a look. Up to the depth of Z equal to d/2, ESWL is P, because both are acting independently. And beyond 2s, more than 2s, equivalent wheel load will be 2P. And between d/2 and 2s, we have to compute it by means of the log. So already I told you you need to find out the interpolated value by means of the log. So here what is the value associated this? It is P, whereas it is 2P, and here it is d/2, whereas this is nothing but 2s. So interpolate and put everything in terms of log. So log 2P minus log P means this vertical distance between the two. That means the height of the line, vertical distance. And similarly 2s minus d/2 means horizontal distance. Both are kept in a log. And similarly log of z minus d/2 means this is z, and this distance will be the z minus d/2. And accordingly you will get the value corresponding to P1, which is called ESWL. And do not try to remember by heart this equation. Always try to understand by means of the curve. So this is having a 2s horizontal and also 2P coordinates, whereas it is having the coordinates of d/2 and also P. And while computing any intermediate values, use log term for various parameters, so that you can find out the equivalent single wheel load. Then normally the design life for flexible payments is 10 to 20 years, and for rigid payment is 20 to 30 years. It is for the rigid payment. It's a normal design life for the structure for the payment. So here type of loads normally the maximum axial load considered in case of flexible payment 80 to 8,200 kg is the standard load. Standard axial load. Standard axial load means this is one wheel and it is another wheel, and these two are connected by means of the axial. This is called the axial. The load that is transferred through this will be 8,200 kg. So the reaction at the wheel or otherwise wheel load will be equal to 4,100 kg. 4,100 kg. So either you can you can see it in terms of axial load. Axial means both the wheels, two wheels will be there on either side. And wheel load means it is the load that is transferred through the one wheel only. And you can look at maximum equivalent single wheel load is 4,100. And similarly for rigid payment, this is the standard value 10,200 and 5,100 kg. So here we can normally call it as 82, you can call it as 82 kilonewtons. So 8,200 kg means 82 kilonewtons. Because we are now using SI system, it's 82 kilonewtons, or otherwise it can be taken as 8.2 tons. 8.2 tons as the standard axial load, or 82 kilonewtons as the standard axial load. So we have to compare all other axial loads with only the standard axial load, because for all computations we use standard axial load, and basing on this only we are going to found the various equivalent factors with respect to the standard axial load. So sometimes for the sake of simplicity we may consider it as 80 kilonewtons, or otherwise we may consider it as 8 tons. So but exact value is 8,200 kg. And these are the single things. Sometimes what is going to happen for the vehicle, this is the type of arrangement that will be there. These two wheels are called the tandem wheels, tandem axles. And this is one axle on the other side. This wheel is connected to the one more wheel on the other side. It is also connected to the another side. Such a system is called the tandem axles. Both the axles are side by side so that more factor. What is the effect of any wheel load or any axial load, any wheel load or any axial load with reference to the actual load that is acting on the pavement? So basing on that, we can find out the equivalency factor. Equivalency factor. That equivalency factor or EILF. Yes, stand if the load on the pavement is say 3,600 kg. So what is the equivalency factor in terms of the standard wheel load? Standard wheel load is 4,100 kg and EF is computed as 59.1. So that means the standard wheel load, if you consider this as a damage factor is 1, because 3,000 kg wheel load passing on the pavement is only 0.594. 0.594. So that means the effect of lower load is much less, and at the same time you can look at it is almost 40% reduced. Effect is 40% reduced, but the ratio is not that 40%. Similarly, if the load is more, let us assume that it is axial load, not wheel load. Say axle load, axle load, actual axle load 10,000 kg and standard axle load 8,000 kg, and accordingly it will be 2,000 2.212. You can see the difference between these two loads, very small difference, only 2,000 kg or otherwise 20%, whereas equivalency factor is more than two times. That means the damaging effect of 10,000 kg load is 2.21 times when compared to the standard load. When compared to the standard load. So, for example, let us assume that the standard wheel loads are passing on a road, say 1 million. Let us consider 1 million axles, 1 million standard axles. If 1 million standard axles of standard load is passing on the road, let us assume that the road is going to damage. So what is the equivalency for it? The same number of repetitions, if 10,000 kg loads are passing, then it will become 2.212 into 10 power 6 million standard axles. So that means it's simply equivalency factor means it is a damaging factor. So when a load of 10,000 kg passing on a highway, it damages 2.212 times the damage of the standard axle load of 8,000 kg. That is the meaning of equivalency factor, or otherwise EALF. Now, sometimes on a road, on a highway, different axle loads are passing. So let us assume that 3,600 axle load vehicles or 2,000 number are passing per day. 4,100 kg wheel loads are passing 100 numbers. 5,200 kg axle wheel load 60 numbers. So here the different magnitude of the wheel loads are there. So we need to compute the in terms of the standard value, because we cannot simply count 200, 100 and 60, total is 360. That is not correct, because the effect of 3,600 is less. Effect of 4,100 is standard, that is 1. Effect of 5,200 will be more. And you can look at here equivalency factor for standard axle load, standard wheel load is 4,100, it is 1. Whereas for 3,600 it is 0.594. That means 3,600 divided by 4,100 whole power 4. That is called the equivalency factor. And similarly for 5,200, it is 5,200 by 4,100 whole to the power of 4. That will be 2.587 times. So now says different weights of the vehicles are passing, wheel load vehicles are passing. Now it is required to find how many equivalent number of standard vehicles passing on the road. That means we are going to convert 3,600 kg wheel loads into 4,100. 5,200 kg wheel loads also converted into 4,100, because 4,100 is the standard load that is considered. So what you do, 200 multiplied by this equivalency factor, 100 multiplied by equivalency factor 1, 5,200 corresponding value 60, 60 multiplied by equivalency factor. So total number of vehicles are 374 vehicles per day. That means this number is 360. That means total number of vehicles passing on a highway is 360, but with different magnitudes of the wheel loads. And if you calculate the equivalency with reference to the standard vehicle, 360 vehicles are not passing, 374 vehicles are passing at a standard axle load of 4100 kg. So that is the meaning of it. And for analysis, we need to compute equivalency in terms of the standard values always. Already in the last class we have seen it, P1 N1 equal to P2 N2, number of P1 is the axle load or otherwise wheel load, N1 is the number of repetitions, and the effect of these two will be the same. So if P is less, N should be more, P is more, N should be less. Accordingly, if the P1 is given as 4100 and 5 million vehicles are passing, then P2 is 5200. How many number of vehicles were passing? So that the effect of it will be the same. It is nothing but 3.94 million vehicles. So that means 5 and center to in tires is say 25 centimeters. Center to center distance between the tires between the ties 25 centimeters. It is not the center to center distance. Okay. So it is clear distance. Clear distance. Okay. It's an example. And D, clear distance between the two wheels is say 25 centimeters. And center to center distance is say 50 centimeters. So this is the data. If this is the data, the possible questions are, yet Z is equal to 10 centimeters, what is the equivalent single wheel load? What is the equivalent single wheel load? So for this, you compare it Z and also D by 2. You know Z is 10 centimeters now considered. What is D by 2? D is nothing but 25 centimeters. D by 2 is 25 by 2. So the first case is well within D by 2. If it is well within D by 2, equivalent single wheel load is 4000 kg. It is nothing but P only. Or the another case is at Z is equal to 125 centimeter depth. What is the equivalent load? These are the possible questions in the exam. If this is the case, compare the value of Z and 2S. Z value is 125 and 2S is 2 into 50, it is 100. So Z is more than 2S. When Z is more than 2S, equivalent single load will be equal to 2P. So 2000, 2 into 4000, 8000 kg is the equivalent single wheel load. At any other level, you know the D by 2 means it is 12.5 centimeter. 2S means it will be equal to 100 centimeters. Below 12.5 centimeter, it is all right. Only the single wheel load P is the equivalent single wheel load. And beyond 100 centimeters, 2S means 100 centimeters. Beyond 100 centimeters, the equivalent single wheel load is 2P, that is 8000. But any depth in between 12.5 and 100 centimeters, then we have to go for interpolation. So that is 80 centimeters. What is the ESWL? So already you know that in the diagram, P corresponding to D by 2, the axial load is P. And what is D by 2? 12.5. What is P? 4000. Everything is in terms of log. And for 2s depth it is load is 2p and log of 100 will be equal to log of 8000. What is our question? Log of Z means log of ESWL. And what is Z? Z is 80 centimeters. Z equal to 80 centimeters now. what is ESWN. So this Z value 80 lies between 12.5 and 100 centimeters. So we have to go for interpolation. This varies linearly, and this is the point in between that, and interpolate the value and get the corresponding thing. So log of ESWL equal to log of P plus log of 2P minus log of P divided by log of 2S minus log of D by 2 into log Z minus log D by 2, and if you calculate that value, you will get 7462 7426.5 kg as the equivalent single wheel load. So this is how we have to compute the equivalent single wheel loads. And these are the things already covered. I'm not going to repeat all these things once again, not required. Now we are in CBR method, and the test procedure and all related things will be discussed in the next chapter, materials. We are not concentrating on the CBR test. We are taking only the CBR value and how it is to be designed. We are focusing only on this. So here the design of traffic is estimated by A is equal to P into 1 plus R whole power n plus 10. A is number of heavy vehicles per day for design. Number of heavy vehicles per day for design. And that number of vehicles will be counted if the weight is more than 3 tons. If the weight is more than 3 tons only, that will be counted. P, number of heavy vehicles per day at the last count. So that means this P means it is present vehicle population, present number of vehicles, and A means anticipated number of vehicles at the time of construction of the highway completed. At the time of construction of the highway completed, A is the anticipation, and this A is found basing on the present population of the vehicle with the growth rate of R. So it is just like a formula related to the compound interest. It is just like compound interest, and you can find out the number of anticipated vehicles at the time of completion of the construction. R is the annual rate of increase of heavy vehicles. And if the value is given, all right. If it is not given, consider 7.5%. Small n, number of years between the last count and the year of completion of construction. I told you in the last class, for example, if the count is in 2020 is P, and if the road construction will be completed by 2022 in another 2 years, that will be called as A. So this A is the number of vehicles, anticipated vehicles at the time of completion of the construction of the highway. That value will be computed basing on the present population of the vehicles, or present vehicles with the rate of growth. You have to remember this formula. It's a normal simple formula. Then CBR method of pavement design by cumulative standard axial load. So already I told you CBR method is adopted by IRC. In Indian Road Congress design procedure, CBR method is considered for the design of the pavements. This formula is more important and you need to remember this. So here based on the concept of cumulative standard axial loads, cumulative standard axial loads. So how many total number of axial loads that are possible? NS will be equal to 365A 1 plus R whole power N minus 1 divided by R into D multiplied by F. So you have to remember this equation. There is no other go. And most of the questions for GATE or any competitive examination are basing on this particular formula. Then NS, cumulative number of standard axial loads in million standard axles. Normally the number will be more, so that's why we call it as million standard axles, MSA. So that means that NS will be represented in terms of 10 power 6. So 10 power 6 means 1 million, and our answer always in million standard axles. A, number of commercial vehicles per day considering the number of lanes, or annual rate of growth of commercial vehicles. N, design life of pavement. D, lane distribution factor. This D is called lane distribution factor. If the lane distribution factor is not given, take that as 1. If it is given appropriately, it is to be used. F is vehicle damage factor. For example, here this formula is used for computing the cumulative standard axle load. If the wheel loads are more than the standard axle load, then damage factor will be more than 1. If the wheel loads passing on highway are less than the standard axles, then F value will becomes less than 1. So already you know how to calculate the damage factor F that you have seen earlier. That is to be computed. F is called the vehicle damage factor equivalent to the standard axles per commercial vehicles on the road stretch. So here, just before going to this, you can also have a look on previous discussion. This is called the vehicle damage factor. Vehicle EALF equivalent axle load factor is this, W by W standard whole power 4. Vehicle damage factor, F1 number of vehicles, F1 number of vehicles, frequency, F means frequency, F number of vehicles of WI are passing. So you can write F1, W1, F2, W2, like that, FN, WN. So that means W1 weight of vehicles 100 numbers, W2 weight of vehicles 45 numbers, WN number weight of vehicles 58. So like that, how many number of vehicles are passing with what is the weight, that is the data here. So basing on this, we can find out the vehicle damage factor. Vehicle damage, if only single vehicle is passing, EILF is nothing but equivalency factor, that is called the damage factor for only one vehicle. But here several vehicles are there with different magnitudes, the different magnitudes of the axle loads or wheel loads, and accordingly we can find out the vehicle damage factor. So WI is the axle load, WSTD standard load, then FI is the number of passes of ith vehicle, and FI will be the sigma FI is the total number of passes. So this is how we need to calculate the F value, and it is to be used in the formula for computing NS value. So here this F is nothing but the value that is now discussed. And lane distribution factor. Lane distribution factor D is 1 for single lane two-way traffic. Single carriageway means no divider. That's all. Single carriageway, no divider. If the road is this is one way and it is allowed two-way traffic, then distribution factor will be 1. Because the entire traffic is going to distribute on the a single lane itself. So that's why it is 1. But in case of two-lane, two-way traffic, what is going to happen? Some of these vehicles are moving in one direction, it is moving in one other direction. Sometimes these vehicles may cross in that way. So if this is the situation, if the lane distribution factor is considered as 0.75. And in the four lane single carriageway. Single carriageway means there is no divider at all. All the vehicles, the vehicle that is here can come to this lane also. So in such a case, the distribution factor will becomes equal to 0.4. And this is four lane two-way traffic dual carriage. Dual carriage means this is one side and it is another side, and in between it is median or divider. So only the traffic on one side will move, and the remaining traffic will move on the other side. So here in this case also D will be considered as 0.75 times, because what is going to happen, the vehicles are moving in the lanes like this. All vehicles may not move in that lane only. All vehicles may not move in this vehicle in this lane only, because while passing, some of the vehicles from lane 1 will come to lane 2, and some of the vehicles passing in lane 2 will also move to lane 1. So that's why the distribution factor considered here as 0.75. 0.75. Now, it is four-lane, two-way, dual carriageway. Four-lane, two-way, dual carriageway, it is also 0.5. Then six-lane, two-way, dual carriage. Six-lane. So in case of six-lane, you can look at here, this is called the dual carriage. Dual means divider. So this is lane 1, lane 2 and lane 3, and lane 4, lane 5, lane 6. In this case, what is going to happen? The distribution factor is going to be less, because some of the vehicles moving on lane 1 is also coming onto the lane 2, but the chances of coming to another lane is very less. So that's why distribution factor here is 0.6. Whereas in case of four lanes on either side of the divider, then the distribution factor is reduced to 0.4. 0.4. That means, what is that we are considering? That four number of lanes are there, and we are going to calculate the total traffic A. Total traffic A. What is the traffic in each lane considered? 0.4 times A. This is 0.4 A, this is 0.4 A, 0.4, 0.4. How much is it totally? 1.6. We are considering it 1.6. So that's why the distribution lane factor for more number of layers will always be less. And here the A is the total traffic, and the number of vehicles passing on this means multiplied by 0.6. Actually the A will be passing equally, assuming that it is equally in lane 1, lane 2 and lane 3, but it is not going to become equally, and 0.6 considered means 0.6 or 0.6, 0.6. That means 1.8 times of the total traffic is being considered in this case, because the vehicles are moving from one lane to the other lane. So that's why we are considering more than the actual count of the vehicle on the highway. You can look at 0.6 and also 0.4. So these are the appropriate values, and you need to understand and appropriately remember, because it's 1.75, 0.6, 0.4. Four different numerals are there, and you can easily understood for computing this. Then, so here the traffic in the year of completion, is estimated as, in the year of completion is estimated as P into 1 plus R whole power X. So actually in previous formula you have seen it as P into 1 plus R power n plus 10. So yeah, 10 is the design life of the pavement considered. It may be 10 years or 15 years or in between any value. And n is the period of construction of the highway. Period of the construction of highway. So now, and this A is after after 10 years of completion of the construction. So 10 means what is A here? The meaning of A is the number of vehicles after 10 years of the construction of highway. Whereas in this case, A equal to P into 1 plus R whole power X, either you can use X or small n or any other parameter. X means here number of years between the traffic count P, between the traffic count P and the year of completion of the construction. Year of completion of the construction. So normally the year completion of the construction will take sometimes 1 year or maximum 2 years. And X may become 1 or 2 depending upon the importance of the highway. Then that is the important method. CBR method of design of flexible pavement is an important one because IRC recommended method is CBR method, and several other methods also there. And you don't try to remember many of the formulas here. Just I'm giving you only the outline of it. Only the outline of it. California resistance value method. So do not by heart this formula. You know that this is one formula, and here it gives directly the total thickness of the pavement. Total thickness of the pavement. TI means traffic index. Traffic index, which is 1.35 into EWL power 0.11, and R means stabiliometer resistance value, and C cohesometer value. So this is the equation, and don't remember this equation because in the examination most of the questions will not be set based on the by hearting formula. So don't try to remember this. Have a look at, have an idea of it, and at the most the questions may be asked in this will be only like this. So C is the cohesometer value. T1 is the thickness corresponding to C1 value. T2 is the thickness of the pavement corresponding to C2. At the most, if at all a question appears in the exam, that is based on this only. So that means out of these 4 parameters, 3 parameters may be given and 4th parameter may be the question. And don't try to remember such a formulas. Several number of such a formulas will come now, and I will put into mark. Don't remember those equations. It is only to have some idea about the flexible pavement design methods. So sometimes a question may be which one of the following is not a flexible method of design? That may be the question. And already you know several different methods, 6 methods are there, and meaning of the methods and overall outer view of the methods is more important. Okay, at the most this is important, and it is T1 by T2 equal to C2 by C1 whole power 1 by 5. That means in the formula T is inversely proportional to C power 1 by 5. So at the most it may be the question in the exam, and not required. Just you will get some idea purpose only, not for the exam purpose. And it is another method, triaxial method. Don't remember this formula. Only thing, triaxial method is used for design of the flexible pavement. That line is more than enough in this particular case. Don't remember this equation also. And with all these equations also not required. But at the most, this equation may be the question, if at all a question appears on triaxial method, here it will be T1 by T2 will be equal to E2 by E1 whole power 1 by 3. So sometimes what is going to happen, some thickness T1 is given, E1 given, T2 is given, what is the value of E2. So for that purpose, if you try to remember this equation and not the remaining, all these things are not required, don't remember. And McLeod method is this, don't remember the formula. If at all a question appears in McLeod method, they will provide you the formula also along with the question. If the formula is given along with the question, then you can substitute the values and you can get the required parameters. Then Burmester method, layered system. Here also don't remember anything, not required. These are the only the methods. You need to remember the different names. That's all about it. Then design of rigid pavements. Design of rigid pavements. So here cement concrete pavements represents as the rigid pavements, and you know the cross section of this. It is subgrade existing soil, and over that subbase course, and above it base course. After that it is concrete pavement. So this is the overall cross sectional view of the rigid pavement. Load carrying capacity is due to rigidity. Already I told you flexural rigidity of the pavement will be more, EI. Moment of inertia is more, and modulus of velocity also more. And it is having high modulus of elasticity, and the load transferred is by means of the slab action. Whereas in case of flexibility method, pavement, in case of flexible pavement, the load transfer is by means of grain to grain distribution. Whereas here load transfer is by means of the slab action. And upward reaction is proportional to the deflection. So P is proportional to the deflection. K, modulus of subgrade reaction. Then Westergaard's method, Westergaard's modulus of subgrade reaction. So this term is more important here. Modulus of subgrade reaction is K, represented as K, which is defined as pressure sustained for unit deformation of subgrade at specified deformation or pressure level using specified plate size. So in this particular method, for computing the modulus of subgrade reaction, what normally we'll do is a plate of 75 centimeter is taken. A plate of 75 centimeter is considered, and the load is applied on it. When the load is applied on it, and this entire plate is going to deform, entire plate is going to deflect vertically by 0.125 centimeter. The corresponding pressure is called the modulus of subgrade reaction. So you can look at here, it is defined as K equal to P divided by delta. P is the pressure corresponding to 0.125 centimeter, or otherwise 1.25 mm deflection. So it's an important bit. So modulus of subgrade reaction is computed for observing the settlement of the plate, standard plate of 75 centimeter as 1.25 millimeters or 0.125 centimeters. So at the time when it deflects, when it penetrates for a 1.125 centimeter, the associated pressure divided by delta is called the modulus of subgrade reaction. You can look at here, P is the pressure sustained in kg per centimeter square by the rigid plate of 75 centimeter at a deflection of 0.125 centimeter. The modulus of subgrade reaction is given by. So it's the most important one. Each and every word is important. 75 centimeter plate standard is important. Delta 0.125 centimeters and K equal to P by delta, which is kg per centimeter cubed. And the pressure deformation characteristic of rigid pavement is a function of relative stiffness of slab to that of slab grade. So now what is going to happen? Normally the same plate may not be available. Say while testing the subgrade for computing the modulus of subgrade reaction, sometimes the soil may be in soaked condition. The soil may be in soaked condition, or sometimes 75 centimeter big plate may not be available. The available plate may be say 30 centimeters. If 30 centimeter plate is available, it can also be tested, but appropriate corrections are to be taken. And at the same time, when the soil is under soaked condition, we have to go for appropriate correction. So here now correction for modulus of subgrade reaction. The possibilities of correction is correction for subsequent soaking condition of subgrade. When the subgrade is in soaking condition, we have to correct the value of the subgrade. So with the standard procedure, you will compute the magnitude of the K value. You will compute the magnitude of the K value. And for the soaked condition, Ks, modulus of subgrade for soaked condition, Ks will be equal to K into Ps by P. Ps by P. So here you need to the pressure under normal condition, pressure under soaked condition. Pressure under normal condition, soaked condition. So in the examination, the possibility of questions, the three of the four parameters may be given. The fourth parameter may be the unknown parameter to be computed for the question. Another correction is plate size. So 75 centimeter diameter plate means it's a big size plate. All the time it may not be available at the testing place. And if the plate diameter is less, then follow the same procedure and correct it for the original standard diameter of the plate. So what normally we do, a heavy reaction load is required for soil with a high K value when plate diameter is 75 centimeter for testing. Sometimes plate may not be available. Sometimes when the subgrade is very hard and very high load is required to penetrate 0.125 centimeters. In such a case, smaller diameter of the plate can also be used, and accordingly K1 computed K1. K1 is modulus of subgrade of smaller size plate. So that means K1 is the modulus of subgrade reaction corresponding to 30 centimeter plate. That is available plate. A1 is diameter of the smaller plate. Whatever the plate that is being tested, associated diameter is called the A1. K is the original modulus of subgrade as per the standard size of the plate. And A is the diameter of the standard plate, which is 75 centimeters. So K can be computed as K1 A1 by K. So that means with the available plate, you can find out K1. You know the A1 value, and A is standard value. You can compute the modulus of subgrade reaction for the standard plate. So sometimes such a small questions may be given in the examination. Next one, radius of relative stiffness. Radius of relative stiffness. And you have to remember this particular formula. It is an important one. L is equal to EH cubed by 12K into 1 minus mu square whole to the power of 1 by 4. You have to remember this formula. L is radius of relative stiffness. Radius of relative stiffness. So that means radius of relative stiffness means the wheel load will be acting at this particular level and it is a thickness, and here it is going to deflect to certain level, and the radius correspond associated with that will be radius of the relative stiffness. Originally the load will be acting on this particular area, you know that this is the big size of the rigid pavement, big size of the rigid pavement. In that, this is the load, and this load will be distributed to the surrounding area, and it gets deformed. The displacement will be there in the rigid pavement. So if the displacement is up to this particular level, then it is called the radius of the relative stiffness. And beyond that, there is no displacement. So displacement will be there from the load it is acting to certain distance, and that is called the radius of the relative stiffness. And you have to remember this formula, and E is the modulus of elasticity of the cement concrete. Mu, Poisson's ratio. H, thickness of the slab. K, modulus of subgrade reaction kg per cm cubed. So just now you have seen this is called K. So with all these parameters, you can find out the radius of the relative stiffness. That radius of the relative stiffness means it is the radius over which the deformation takes place. So here the load area deformation is more, and as it is away from it, deformation will be less, and the deformation will be something at the outermost point, and beyond that there is no deformation. So that radius is called the radius of the relative stiffness. And it's an important equation you have to remember. Then stresses acting on the rigid pavement are. What are the various types of stresses acting on the rigid pavement? So here what are the types of forces that are acting? One is wheel loads. Wheel loads are acting on the pavement. So stresses due to wheel load will induce in the pavement. Another one is temperature stresses. Because it is a single unit, it's a rigid, naturally temperature stresses will induce under certain conditions. Whereas in case of flexible pavements, there is no stresses induced because of the temperature. Whereas in the case of rigid pavement, the temperature stresses induced due to variation of the temperature. It may be rise of temperature or fall of temperature. So we have to analyze now and understand fully about the wheel load stresses and also stresses due to the temperature. And after that, once you know the stresses at different levels, it is necessary to understand the critical load positions. What are the critical load position? The load may be, wheel load may be at the interior. Load may be at the interior. So if the load is at the interior, the stresses associated at that point are called the interior stresses. And sometimes the wheel load while passing, the load may be at the edge, top edge. Then it is called the critical, another critical position is edge. So the stresses developed because of the wheel load at the edge, those are called the stresses, edge stresses. And another case, the wheel load may be at the corner of the slab. So these are the three important critical positions that we need to calculate the stresses. So that means stress at interior, and we can call it as a sigma I. So stress at edge, sigma E. Stress at corner, sigma C. So these are the three different stresses. These are the three different stresses that are coming into picture for the position of wheel loads. So now here we can look at interior loading means loading is at interior. Edge loading means it is one of the edge. Four edges are there for the slab. Four edges are there. When the load is applied on the edge of the slab, at any place remote from the corner. So other than the corner, at any point load is acting, it is called the edge loading. And another one is corner loading. Load acting at the corner of a slab, corner loading. Now, equivalent radius of resisting section. Equivalent radius of resisting section. So you know at the top, at the top of the slab where the wheel load is acting, the radius of the relative stiffness is say L. And resisting section, equivalent radius of resisting section, this load is going to distribute to the underneath the soil, and this is the radius of the resisting section. So here B means equivalent radius of resisting section. So this distance is called the B value. And it depends on B equal to 1.6 A square plus H square minus 0.76 X. So don't remember this. All these things are not required. You need to understand the meaning of several other things. So don't remember all these things, not required. Just you should know what is equivalent radius of resisting section, what is the value of the L, but L value is more important. You need to remember the formula. Next, wheel load stresses. Because of the wheel load, the load can occupy at the interior, edge or the corner. Accordingly, the stresses will develop. So, when the load is exactly at the center, say for example, this is the cross section of the slab. When the load is acting exactly at the center, it is going to deflect in this fashion. So because of the wheel load P, the bottom surface is under tension, top surface is under compression. So you can look at here, it is written tension at bottom. So tensile stresses are induced at the bottom, compressive stresses are induced at the top due to center loading, due to interior loading. And similarly, even the load is at the edge, so here also the same thing, because it is also going to deflect in this shape, in this fashion. Naturally, the tension at bottom and compression at top. Whereas when the load is at the corner, for example, imagine that it is a cross section and the load is acting at this level, then there is every possibility that it is going to bend like this. When the load is acting at the corner, the possibility of bending of the slab is in this fashion. So bottom is under compression, top is under tension. So you can look at tension at the top. So remember, at corner, tension occurs at the top. And for the interior load and also edge loading, the tension occurs at the bottom. Tension occurs at the bottom. So this is more important where the tension occurs at the top or bottom because of different types of loads. That is more important. And don't remember the formula. No formula is important here, and it's very difficult to remember these formulas. Westergaard's stress distribution equation for wheel loads given interior loading, edge loading and corner loading. And it depends on the radius of the relative section and also B equivalent radius of the resisting section, axial load and also thickness of the pavement, etc. And it is not possible for you to remember, and in the examination also the questions are not with these formulas. If at all a questions will be asked from these in the examination, they will provide you this formula also. For example, here stress due to interior loading is a question. So along with the question, this formula will also be given, and you need to substitute L, B, P, H appropriately and compute the value of the SI. That is the possibility in the examination. But don't try to remember any of these equations. Only at the most you can remember the stress depends on the axial load, thickness of the pavement, radius of the relative section, then radius of the resisting section. These are the various parameters. That is more than enough, and don't remember the formulas. And of course, meaning of all these here, S is the meaning of stress. SI means stress interior. SE means stress at edge. SC is the stress at corner. And sometimes the numerical questions may be given, but they will provide you the required information and they will ask the questions relative to the other information. And this is IRC formula. Don't remember these formulas. It's only I am showing all these things only to get some idea about the loading, external loading. And this is more important. You have to remember this EH cubed by 12k into 1 minus mu square whole to the power of 1 by 4. That's all about the stresses. So loading stresses, no numerical question directly will appear in any of the examination because the formula itself is tedious and computation is not possible for you to do the same in the examination. So that's why they will provide you all information, then you can calculate the things. And their important thing is, because of the loading at the interior and also the edge, bottom face is under tension. And because of the corner loading, top face is under tension. So that is more than sufficient now. Okay. Now temperature stresses. Temperature stresses are developed due to variation of temperature in slab. So at the bottom of the slab one temperature, at the top of the slab another temperature. Sometimes the temperature may be uniform from bottom to top also at certain point of time. But in general, the variation will be there from bottom to the top. And normally we can call it as daily variation. Daily variation means variation of temperature across the depth of the slab. Daily variation. So from morning to evening to night, the top temperature is changing, bottom temperature also changing in the day and also in the night. There is no constant. So variation of the temperature daily. So that is called the daily variation across the depth of the slab. Seasonal variation. That means overall increase or overall decrease of the slab temperature will be basing on the seasonal variation. And during the day, top of the pavement, high temperature. The high means more temperature. During the day, top of the pavement is subjected to more temperature than the bottom. Bottom is lower temperature, top is higher temperature, that you know, during the day. And during night, top is low, top is less, and bottom will be more. It is just like reverse on the day. So in the daytime, if you call it as it is in the day, so at top it will be more and bottom is less. And for the slab in the night, top it will be less and bottom the temperature will be more. Temperature relatively more, not absolute values. Relatively more than the top of the slab. So here we have to find out the maximum possible worst cases. For maximum possible worst cases means maximum possible magnitudes of the tensile stresses induced in the pavement. So maximum difference in temperature between top and bottom of pavement slab occur at some period after the mid-noon. So after 12 o'clock, maybe around 2 o'clock, the maximum difference of temperature between the top and bottom occurs. So at that particular situation, the worst magnitude of the stresses will induce. And what is going to happen here when the temperature is difference is there? Normally when the temperature is uniform, from top to the bottom, what is going to happen? This is going to increase uniformly. If it is allowed free, If it is allowed free. But here, due to the variation at top and bottom, warping of the stresses will come into picture. So the entire slab is going to bend in this fashion. The entire slab, because of the temperature, warping occurs. Warping occurs in this particular level. Okay, so this we can call it as warping up, and we can call it as warping down. Warping up and warping down. Warping up, warping down. So this warping, just observe here that there is a difference of temperature top and bottom. So since the temperature at the top will be more during the day, it will take the shape like this. That means warping down is on the day. Warping up is on the night. So this wording is more important. So here you can look at warping occurs due to difference in temperature. Where the difference? Due to difference at the top and bottom. If the temperature top and bottom is same, it is going to deform horizontally and there is no warping. Warping will not occur. But here, change of temperature exists between top and bottom. Naturally, warping of the slab occurs. During summer, what is going to happen? Concrete pavement expands. If the space is available, it is going to expand freely. Normally, what is going to happen? Between the pavement slabs, we are going to keep mastic pads so that it will allow to expand. It will allow to expand. If any expansion is prevented, if any expansion is prevented, compressive stresses will induce. So remember, in summer, temperature is more, and it tries to expand. If the expansion is prevented, compressive stresses induced. Compressive stresses induced. And during winter, concrete pavement contracts because temperature is less. When the concrete pavement contracts, what are the stresses induced? Tensile stresses are induced in it. What is going to happen? You just look at this. It is original length, say L, and say this is delta L or simply delta. If it is allowed freely, no stresses induced. If it is allowed to expand freely, no stresses induced in the slab. But here what is going to happen? This expansion is going to be prevented. How it is going to be prevented? By means of developing compressive stresses in it. Compressive stresses in it. So remember here, summer, it try to expand, and because of the prevention of the expansion, compressive stresses are induced. And in the same way, during winter, temperature is less, concrete contracts, and tensile stresses will develop. Tensile stresses will develop. Okay. Now, this is the natural case that we can look at during the day. During the day, what is going to happen? During the day, T2, say for example, temperature 2 at the top and temperature T1 assume at bottom. So what is going to happen? Top surface is going to increase. So it is subjected to compressive stresses. Bottom surface is going to increase less. So it is subjected to tensile. And similarly, during the night time, T2 is less than T1 and the stresses induced are reverse. Frictional stresses are developed due to seasonal variation in temperature. So in general, because of the temperature, two different types of stresses induced. One is warping stresses. Another one is frictional stresses. Warping stresses induced because of the warping of the slab. Because of the warping of the slab. So by warping of the slab in these two directions, then stresses induced in it, those stresses are called the warping stresses. Another one is frictional stresses. What are the frictional stresses? Assume that it is the center line of the pavement. If the temperature is more, what is going to happen here? It is going to expand. It is going to expand. But because of the friction induced at the bottom of the pavement and the layer, what is going to happen? It is going to prevent that expansion. It is going to prevent the expansion. It is going to expand. That expansion is going to be prevented by this, and the stresses induced at the bottom are called the frictional stresses. Frictional stresses. So, because of the temperature, two types of stresses induced. One is warping stresses that will occur because of the warping of the pavement. Another one is frictional stresses. The friction, the resistance offered between pavement and the subgrade is trying to prevent the expansion, or is trying to prevent the contraction also. In such a case, frictional stresses will induce at the bottom. Frictional stresses will induce at the bottom. So here there are two different types of frictional stresses again. Okay, before that, we will come to later. Now let us discuss in detail about the warping stresses. Warping stresses. When top and bottom surfaces of concrete possess different temperature, the slab tends to warp downward or warp upward. Warp downward or warp upward. So this is called the warp down, and whereas it is called the warp up. It is because of the change of temperature between top and bottom. And don't remember this formula, not required. It's only to give some idea regarding this. And you can remember this. It's a normal thing. Warping stresses at the edge region. Warping stresses at the edge region. You know that in normal temperature stress will be equal to alpha T into E. Alpha into T into E are the temperature stresses you have studied in strength of materials. So now here alpha T into E, you can look at alpha T into E into coefficient in x direction divided by 2, or otherwise coefficient y divided by 2, whichever is higher will be considered as the edge stress. Remember this equation, it's not a difficult one because half of the slab will be effective. So if you consider in this particular direction, only half is effective. So coefficient multiplied by half alpha TE by 2. One is multiplied with Cx, another one is multiplied with Cy. And this is the graph showing the values of Cx and also Cy. So sometimes the question may be given and Lx by L, Ly by L, the ratio basing on that for this from this particular graph, you can find out what is Cx, what is Cy. For example, for Lx by L equal to 6. If it is 6, what is the alpha x value? Alpha x value will be somewhere here, which is equal to 0.85. And similarly, Ly by L is say 4. 4 means the corresponding value will be equal to 0.5. So sometimes in the examination, instead of giving data, they may provide you the chart or table like this. Then you can also read the values corresponding to that one. And here it is warping stress at the corner region. Don't remember this also. So all these formulas just I am giving you only the outer knowledge sake, but not for the examination purpose. So these two equations are important. You need to understand it. Stresses because of the edge. Temperature, stresses due to temperature at the edge. Then frictional stresses. Frictional stresses. So here frictional stresses, just you can look at this diagram. This is the cross section of the slab. And when the temperature is more, it is going to rise, increase it. But because of the frictional resistance between the slab and the pavement, so between the pavement and also the subgrade, then what is going to happen? This expansion is going to be prevented by means of developing the friction. Preventing by means of the developing the friction. And what type of stresses developed here? Compressive stresses developed. Compressive stresses induced. So compressive stresses induced. That means in summer, what type of what type of stresses induced because of the friction? It is only the compressive stresses. Whereas in case of winter, the temperature is going to become less. So original slab edge is going to reduce now, and since it is moving towards the center, the frictional resistance will be in the opposite direction, and because of this, tensile stresses induced in the section. Tensile stresses induced in the section. The maximum tensile stresses occur at the center because all these frictional forces are acting at one point, second point, third point, etc. And maximum will be at the mid span, maximum at the center. So the maximum frictional stresses will occur maximum at the center of the slab, at the midline of the slab, not the center, overall center. It is midline of the slab or even edge also. From this edge to that edge, it may be center or one fourth or even the edge. So maximum frictional stress will occur at the center. And what is the frictional resistance at the edge, at this particular edge? Frictional resistance at this edge is equal to 0 because that is the free point. There is no much thing to move and there is no much resistance. The resistance will be more and more as it is coming towards the center, because all these forces are acting about the center, but the force acting at the edge is 0 here, very small. In the corner it is always 0. So that means at corner of the slab, the frictional stress, frictional stress is always equal to 0. But at the edge, some frictional stresses will be there. Because if you consider in this direction, the stress may not be there. But perpendicular to the direction, there will be some stresses. So that means frictional stresses are available along the edges and also at the center of it. So at the center, the stresses are maximum. And in summer, the compressive stresses induced because of the friction. In winter, the tensile stresses will induced in the pavement. So this is the overall concept. In the examination also, the questions will be whether compressive stress, tensile stress, summer, winter, day, night, these are the various terms associated with it. Now, frictional stresses. Now let us compute the what is magnitude of the frictional stress. Already you have seen the diagram. Already you have seen one diagram. So this is the overall. So this is the overall slab, and this is the center part. What is going to happen if it is going to expand in this direction? It is going to expand in this direction. The frictional stresses will be induced at the bottom in the opposite direction. This is called SF. This SF, frictional stress. And at what level the frictional stress will act? You know that here it will be, say, this is B. No, this is length. And you know, this is width of the section. And also the thickness of the section is H. So the size of the panel is L into B multiplied by H. L is the length, B is the width, and H is the thickness. And where the maximum stress is acting? Maximum stress is acting at this particular level, at the center. And what is that maximum stress? Maximum stress is nothing but SF. You can look at the total force developed in the cross section of the pavement due to movement is stress multiplied by area. What is the area? The area will be equal to cross sectional area. What is that cross sectional area? B multiplied by height. So B multiplied by height, and that is the total force developed at the cross section. What is the frictional resistance? Frictional force or frictional force is, this is the frictional resistance. What is the frictional force? Frictional force is nothing but F is nothing but mu multiplied by W. Frictional force is always normal to the direction of the normal force. If the W is the weight of the force, that what is the weight of the force? Here W means weight of the slab and mu is coefficient of friction. Coefficient of friction. Of course, here instead of mu, we are calling it as F. We are calling it as F. So F is equal to F into W. So what is W? W means weight. Weight means volume multiplied by density. Volume multiplied by density. What is the volume of this entire slab? Volume of this entire slab will be B. You can look at this is B and L by 2, only half of the length multiplied by height. This is called the volume of the slab. That is multiplied with the density of the slab. So that is called the total weight. Total weight multiplied by frictional coefficient. Coefficient of friction is F. So this is the frictional force due to the weight of the concrete. And this will be equal to the resistance. The resistance is by means of SF into HB. Accordingly, you can find out this. Don't try to by heart this formula. Sometimes this may be the question, numerical question in the exam. But if you by heart this formula, the reproduction of the same in the exam may not be possible. So for that, always try to understand SF is the frictional stress induced in the concrete multiplied by cross-sectional area B into H. And another one is W multiplied by F. What is W? B into L by 2 into H into rho, that is weight multiplied by F. From that you can derive this equation. So in the examination, always try to derive this equation, not by means of by hearting this equation. Of course, already completed. Next, combination of the stresses. Combination of the stresses. So we have to look at various worst combination in during summer. What is the possible worst case? We can call it as critical combination of the stress. Critical combination of the interior and edge regions during midday occurs when the slab tends to warp down. When the slab tends to warp down. When the slab tends to warp down. So what is going to happen in midday warping will occur like this. Warping down. Okay. This is in day. Already I told you earlier, in the day it will be warped in this particular direction. Maximum tensile stress developed at the bottom due to warping. Then frictional stress is compressive during expansion. So here, when the slab is in a horizontal, because of the wheel load, it is going to develop the stresses. Bottom is under tension. That means load stress is under tension at the bottom. Load tension is under tension at the bottom. And remember, warping stresses are in the same direction as that of the load stress in worst cases. And frictional stress is always opposite in direction. Already in the previous section, I told you, during the day when there is a expansion, what is the nature of the stress? Nature of the stress is compressive. That means in summer, compressive stresses will induce. In winter, tensile stresses will induce because of the friction. So what you do here is, a critical combination of the stress is load stress, warping stress minus frictional stress. Because in summer, we are now observing in summer, the stress induced in the pavement will be compressive stress. So that's why it is minus. So one possible combination is during summer, load stress, warping stress minus frictional stress. And during winter, worst possibility is load stress, warping stress are in the same direction, and frictional stress is also under tensile. Stress is also under tensile, and the combination of the worst possible case or critical condition is sum of all the three values. Sum of all the three: load stress, warping stress, frictional stress. Okay. At corner region, the load stress and also warping stress. So at the corner already I told you no frictional stress induced. At the corner no frictional stress, only these two. So it's an important part from the point of view examination. Only the three combinations. In summer, load stress plus warping minus frictional. In winter, load plus warping plus frictional. And at corner, load stress plus warping stress. No frictional stress will come into picture. These are the only three cases that you can remember for the critical load, critical stress combinations. In the examination, all the magnitudes of the stresses are given during winter, summer, day, night, etc. Several combination of it. Accordingly, you need to take appropriate values and sum of the three values in case of winter, sum of two values minus frictional in case of summer, sum of load and warping stresses in case of corner region. Now, design of joints in cement concrete pavement. So mainly the design is more important because to reduce the temperature stresses. If there is no joint provided, the entire expansion possibility completely prevented. Whenever the expansion or contraction prevented, the large magnitude of the stresses will induce and warping also maximum, and there is a possibility of developing the tensile cracks, and finally it may not be useful for the intended purpose. This is the overall view of the various joints you can look at. And normally the rigid pavement will be in the form of a slab panels. This is one panel, it is second panel, third panel, fourth panel, etc. And again it is 1, 2 and 3, etc. So now you can look at various joints. This joint, the direction of the traffic is like this. The vehicles are moving in this direction. The joint parallel to the direction of the flow is called the longitudinal joint. You can look at this is called the longitudinal joint. The longitudinal joint is in the direction of the traffic flow. And another joint is called the contraction joint or otherwise the expansion joint. Both are one and the same. These joints are called the transverse joints. You can look at this joint. This joint is called as transverse joint. Transverse joint, or otherwise we can call it as expansion joint or contraction joint, depending upon the situation that arises. So this transverse joint is perpendicular to the direction of the traffic. Perpendicular to the direction of the traffic. And you can look at the entire pavement is divided into longitudinal and also cross joints. So now various different types of reinforcement will be used. Sometimes without any reinforcement the slabs will be casted. So that is completely PCC. Sometimes the minimum temperature steel will be provided in both the directions. Temperature stresses means to distribute the loads evenly to the surrounding parts. For that purpose, temperature steel reinforcement is being used. Otherwise, no need of using the steel reinforcement in these slabs. And again, these dotted lines are the reinforcement in different directions. You can look at dual bars. Dual bars will be provided across the cross section. This is the cross section or transverse section. For the transverse section, the bars that are provided in between the two panels is called the dual bars. Dual bars. So dual bars are provided. You can look at the diameter. The length of the dual bar is parallel to the direction of the traffic, or otherwise the bars are provided in the same direction as that of the longitudinal section. So that means across the cross section, the bars are dual bars. And across the longitudinal joint, these bars are called the tie bars. You can look at tie bars. Tie bars are provided along the length, It is only for the longitudinal joint. So these are the various different parts of the pavement and associated reinforcement required. So here you can look at all these. Dual bars are provided at expansion joints. Longitudinal joints in concrete pavement are constructed with suitable tie bars. So tie bars will be provided along the longitudinal joint. Now spacing of the expansion joints. This is panel 1, panel 2 and panel 3 etc. slab panels, and we are allowing a gap of delta in between the various panels for expansion and contraction of the joints, so that the stresses may not develop in the panel. So delta is the width. So we should use a considerable magnitude. It should not be too low and it should not be too high. If it is too low, then there is a possibility of developing the tensile stresses and temperature stresses. And if it is too high, then when there is a gap, then there is a possibility of damage of the edges because while moving the traffic, and it is inconvenience to the traffic also. So here the width of the gap in expansion joint normally depends on the length of the slab. The use of wide expansion joint space should be avoided. So wide joint should not be recommended because normally it is going to happen, more dual bars are required, and when you use dual bars, there is a possibility of bending and also bearing stresses induced in it. When the bearing stresses or bending stresses induced in large quantities in dual bars, then there is a possibility of damage at the junction. And normally the gap should not be more than 2.5 centimeters. Or normally more than 2.4 centimeters. And already you have studied delta will be equal to L into alpha into T. Length of the panel, alpha multiplied by the difference of the temperature. Whatever the formula that you have seen earlier, the same thing. But in this particular case, normally what is going to happen is, this entire gap is being filled with the filler material. Mastic pads will be provided, and mastic pads will be provided completely. And whenever the expansion is necessary, mastic pads are going to compress, and compression of those will be only delta by 2. Full thickness of mastic pad may not be compressed. So what is going to happen here, though the spacing between these two is delta, is delta, is delta, the joint filler may be compressed only 50%, and the remaining 50% is the only allowed to expand or contract. So that's why expansion of the gap means it is 2 times of the allowable expansion of the joint. So what you do, delta dash will be equal to L into alpha into T. What is delta dash? Delta dash is nothing but delta by 2, which is alpha L alpha into T. It may be delta by 2 or any other numerical value that may be given. So delta dash equal to L alpha T. Basing on this, you can find out L value. What is L? L is the length of the panel, and that is called the spacing between the expansion joints. L is the spacing between expansion joints. When all this information is known, you can find out the actual L value. Similarly, spacing of contraction joints. How much spacing for contraction joints is required? And here in the contraction, maximum stress occurs at half of the length. Maximum stress occurs at the half of the length. So when it is contraction, when there is a contraction, what is the frictional resistance? Frictional resistance is nothing but F multiplied by W. So F multiplied by W means already you have seen B into L by 2 into H into rho into F. You know, this is the weight. Weight multiplied by frictional coefficient. Similarly, allowable tension in concrete. Allowable tension in concrete. So what is going to happen when it is going to contract, when it is going to reduce its value, then tensile stresses will induce and maximum tension occurs at the bottom. So if you call it as F or ST, SF or ST, SF multiplied by cross section. What is that cross section? H multiplied by B, and accordingly you can find out the LC. LC means the length of the contraction joint. Length of the contraction joint. Don't remember these formulas. You should understand the meaning of it. You should also understand the meaning of these two and equate these two. And if it is a question in the exam, and you can develop the equation there, not by means of by hearting. If you by heart this, it's impossible to recollect the same. Okay, this is the only thing. Already I told you the total weight of this. Total weight is nothing but L by 2 into B multiplied by height into rho is one parameter. Rho multiplied by frictional coefficient will be equal to, this is called the maximum stress will develop at this level. So SCF multiplied by this entire cross section. That entire cross section will be H multiplied by B. So from this L is called now, L is called contraction joint distance. Spacing between the contraction joints, LC. So from that you can find out it. Then spacing of contraction joints when reinforcement is provided. So what is going to happen here? Sometimes the reinforcement may be provided at the bottom. If the reinforcement is provided, we are going to assume that entire stresses will be taken care by the reinforcement only. Entire stresses will be taken by the reinforcement only. So you know this is W. What is the force developed resistance? It is nothing but L by 2 B into H into rho into F, which is equal to the entire stresses will be taken care by the steel only. That is it is assumed that the reinforcement takes the entire tensile stresses in the slab. If only the stress is taken, we can write sigma st multiplied by ast, or otherwise ss multiplied by as. SS multiplied by AS. Area of the steel, stress in steel. From this you can find out how much quantity of AST is required, or otherwise what is the spacing of the contraction joint L. Either you can find out L value or otherwise AST value or any other parameter basing on this. Here also don't remember this formula. You need to understand this original concept. From the original concept only, you have to develop the formula when it is required in the examination. Then design of Doyle bars. So what is the main purpose of Doyle bars? Doyle bars allow opening and closing of the joint, and load transfer is effected from one slab to the other slab. So you can look at here at the joints, this is a cross section of one slab, slab 1. It is cross section of the another slab. When the wheel load is passing, and it is at the edge, when the load is exactly at the edge is going to deform in this way, and the entire load is acting on the slab 1 only. There is no load transferred to the slab 2 because there is no Doyle bar, there is no reinforcement in between. But here, when these two slabs are tied with the Doyle bar, the yellow color is a Doyle bar. Yellow color is Doyle bar. That Doyle bar is LD, development length on one side, another side also development length, and in between this gap. What is the total length of the Doyle bar? Total length of the Doyle bar is LD plus gap. Gap means it is delta again plus LD. So that is the total length of the bar. And what is LD? LD is called the development length. Already you know in strength of material RCC has studied LD will be equal to 5 sigma S divided by 4 tau BD. If the bond stress in concrete is known, permissible stress in steel is given, diameter is given, you can find out the development length. So development length plus delta gap between the two slabs, and also again development length, that is the total minimum length of the Doyle bar to be provided. If the Doyle bar is provided between the two slabs, then what is going to happen? The slab 1 is not going to deflect. It will deflect. At the same time, part of the load will be transferred to the slab 2, so that the damage will be less. So for that purpose, the Doyle bars are to be provided at this particular point, and generally it will be from D by 3 to D by 4 height. From the top, it will be provided from D by 3 to D by 4, or H by 3 to H by 4 distance. So without the Doyle bar, there is a possibility of damage of the slab edges, because at the edge it is always weak, and transfer of the load is not for the large area, it is only for small concentrated area, and there is a possibility of failure. And by providing a sufficient number as per the design, the Doyle bars are provided in between, and whenever the load approaches to the edge of the slab, the load will also transfer to the other slab, so that the resultant magnitude of the stress developed will be less. That is the main function of the Doyle bar to be used. And here what is going to happen? This Doyle bar is completely fixed in one slab, and it is free in the other slab, because for the rise of temperature or fall of temperature, this should not be a restraint. So that's why what is going to happen, if this is the Doyle bar in two slabs, in one slab it is perfectly bonded. In one slab it is perfectly bonded, and in another slab there is a gap. There is a gap in between. There is a gap. So that means the bar is going to move towards or away from it. So that during the rise or fall of temperature, this is not going to prevent the expansion or contraction of the slab. And don't remember this. If at all a question from this will be the theoretical question, how the dial bars are provided, what is the function of the dial bar, and where it is provided, etc. And don't remember these formulas also, not required. But it is a simple formula that you can understand what is the minimum length of the dial bar. And this dial bar will be provided at a distance of d by 3 to d by 4 from the top. It is not at the bottom level, it is only at the top level only, d by 3 to d by 4. That means 1/4 of the thickness to the 1/3 of the thickness of the slab. And don't remember this formula also. So minimum dial length is in one side LD plus delta and also LD. Total overall length. Overall length will be LD plus delta plus LD. Okay, design of tie bars. So here tie bars means these bars are provided across the longitudinal joint. These are called the tie bars across the longitudinal joints. What is the main purpose of it? The bars are used across the longitudinal joints of the pavements. Tie bars are not designed to act as a load transfer devices. So these are not for the load transfer. Whereas the dual bars are provided for the load transfer purpose at the edge from one slab to the other slab. Tie bars are designed to withstand tensile stresses. If there is any tensile stress that is acting at that junction, that will be taken care by this. The maximum tensile stress in the bar is equal to the force required to overcome the frictional force between bottom of the adjacent pavement of slab and soil subgrade. So here because of the frictional resistance, sometimes the tensile stresses induced along the longitudinal joint, and those will be taken care by the tie bars. This will be taken care by the tie bars. You can look at here. This is one and this is another one, and it is a panel. Tie bars are provided in this fashion like this. Tie bars are provided like this. So what is the total frictional resistance here? What is the total frictional resistance? Let us assume that here it is for a B into H. It is for a B into H. What is the this is called the width. This is called the width B, and multiplied by thickness. Multiplied by thickness. Multiplied by 1 unit. You consider it as 1 unit. 1 unit means this is 1 unit. Length is 1 unit. And this entire area is 1 into B into height. 1 into B into height into rho multiplied by F. You can consider it as 1 means 1 meter. Say 1 meter. So what is this called? This entire is called the frictional resistance. Now here L will be taken as 1 meter. L into B into H into rho, that is the weight, multiplied by frictional coefficient. That means for 1 meter, this is the frictional resistance. Friction induced. What is the resistance? Resistance is by means of the steel, that is AS multiplied by SS, and from this you can find out AS value. Don't remember this formula, always try to understand this. So here for computing the area of the steel is for a unit length, because longitudinal joint means it may be any length, but when once you know for 1 meter how many number of bars are required, that will be continued throughout the length of the longitudinal joint. So here also you need to establish. So all these formulas, if you try to remember, it's difficult. If you try to understand, it's very easy, and you can answer the questions in the examination. So this is how the steel reinforcement regarding the tie bars. So with this, the entire theory related to the design of flexible and rigid pavements is completed. Let us have some discussion on previous gate questions. It's a very recent question appeared in 2020. For an axial load of 15 ton on a road, 15 ton on a road, that is actual axial load on the road. The vehicle damage factor. So the question is, what is VDF? The vehicle damage factor rounded off to 2 decimal places in terms of standard axial load of 8 tons is. What is VDF value? VDF value will be equal to the actual load divided by standard load. Okay, already formula is there. The whole power 4. You know this formula. W by W standard whole power 4, and this 12.36 is the answer. It's a very recent question in the examination. Then another question in 2020. A dual bar is placed at contraction joint. A dual bar is placed at contraction joint. When contraction occurs, the concrete slab cracks at predetermined locations. Identify the arrangement which shows the correct placement of dual bar and the place of occurrence of the contraction cracks. So normally the contraction cracks occur at the edges, and steel reinforcement will always be provided perpendicular to the crack. Steel reinforcement will always be provided perpendicular to the crack. If the cracks developed vertically, the reinforcement is horizontal. So how the cracks will develop, you can look at here. There is a possibility of developing the crack from bottom to top, and you can provide the reinforcement in this fashion. And there is a possibility of developing the crack from bottom to top, and there is a possibility of providing the dual bar for it. And here you can look at, this is one crack, crack 1, this is another crack. Between the two cracks, there is no possibility of providing the dual bar. Dual bars are required only to prevent the cracks. But here the cracks are at certain distance. The bar is provided between the cracks. If the bars are provided between the cracks, there is no use of it. So reinforcement must be provided perpendicular to the development of the cracks. Here also two different cracks. This is one crack and it is another crack. Two cracks are developed and reinforcement is only between the cracks. So this is also not correct, because whenever there is a crack, the reinforcement should be provided on either side of the crack, so that the tensile stresses or compressive stresses will be taken care by that particular reinforcement. So these two are not correct. And here, regarding out of these two, the reinforcement dual bar must be provided on either side of the crack. So these are the two possibilities. And you know, the main purpose of it will be to distribute the load. When the load is coming onto one slab, and it has to transfer effectively to the other slab, that is possible only when you provide the reinforcement at the top level. When you provide the reinforcement at middle or even below middle, there is no possibility of developing transferring the load from one to the other one. So this is the correct option for keeping the dual bar. So dual bar must be provided across the crack, and it should be at the top of the section only. That is at a distance of d by 3 to d by 4 from the top, not at the middle, even not at the bottom. And dwell bars are not provided between the cracks. It is provided on either side of the cracks only. So it is only by observation. By observation, you can answer the question. And in 2019, a flexible pavement has the following class of loads during a particular hour of the day. 80 buses with 2 axles. So each bus is having 2 axles, and each axle is of load 40 kilonewtons. So such a type of 80 buses are passing. And at the same time, 160 trucks are passing with 2 axles. Front and rear axles are there, but front axle load is 40 kilonewtons. Rear axle load is 80 kilonewtons respectively. The equivalent standard axle load repetitions for this vehicle combination as per IRC would be. So here ESAL is to be computed. What is ESAL? Equivalent axle wheel load. Equivalent axle wheel load is to be computed. You know that it is nothing but sigma Wi divided by W standard whole power 4. And of course, if it is F, use F value also. If the single loads are there, individual loads, it is the formula. Or otherwise, if such a number are there, you can use the EAFL will be equal to sigma Fi multiplied by Wi by WSTD whole power 4. Already this formula discussed today. So now find out the different class of it. For buses, 2 axles, and these 2 axles are same magnitude of loads. So total how many axles are there? 80 buses, 80 into 2, 160 axles. 160 axles, each axle is 40 kilonewtons. Then for trucks with 2 axles, in case of truck, how many trucks are there? 160. 160 trucks means 160 axles of 40 kilonewton load, and again 160 axles of 80 kilonewton load are passing. So the how many now? It is N1 160, N2 160, N3 160 number of axle loads are passing. One is 40, another one is 40, one more is also one more is 80 kilonewtons. Now find out the standard. What is the standard value? Standard value is 80 kilonewtons. Standard value is 80 kilonewtons. Already I told you 8150 or otherwise 82 kilonewtons or 80 kilonewton is the standard. So standard axle is this. So you know the formula, equivalent number of repetitions. Equivalent number of repetitions, it will be already I told you earlier also that this is number multiplied by the equivalent factor corresponding to the standard load 40 by 80 whole square, and again 160 number 40 by 80 whole power 4, again another 160 80 by 80 whole power 4. It will be 10, 10, 160. That means out of all these 160, again 160, again 160, the total it is nothing but 480 axles. 480 axles of different capacity. It is equal to 180 axles of 80 kilonewton load. 180 axles of 80 kilonewton load. That is the question. So equivalent standard axle load repetitions. That means As per the given data, 480 axles are moving. That effect is same as that of 180 axles are moving with a low axle load of 80 kilonewtons. Next one, tie bars of 12 mm diameter are to be provided in a concrete pavement slab. Tie bars. Where tie bars are provided? Tie bars are provided for the longitudinal joint. For the longitudinal joint. The working tensile stress of the tie bar is 230. That is sigma S. The average bond strength between bond and concrete is tau BD 2 MPa. And the joint gap between slabs is 10 mm, delta equal to 10 mm. Ignore the loss of bond and tolerance factor. The design length of the tie bar is. What is the design length of the tie bar? It is nothing but LD plus delta gap again LD. This is the minimum length. We can provide a little bit more than this, but not less than this value. So what you do? You need to find out L value. Delta is given 10, and you have find out the LD value. What is LD? LD is already you know the formula 5 sigma S by 4 tau BD. It is 345. So length of the tie bar is LD plus joint plus LD. It is nothing but 700 millimeters. So this is the longitudinal joint. Along this LD on one side, LD on other side, gap is 10 mm. So that the minimum length of the tie bar is 700 millimeters. And this is a numerical question rounded off to nearest integer. Nearest integer means you have to enter the answer as 700. You can see this. Given the following data, design life n equal to 15 years. Design life n equal to 15 years. Lane distribution factor D 0.75. The annual rate of growth of commercial vehicles are equal to 6%. Vehicle damage factor 4. Initial traffic in the year of completion of construction. You can remember here, initial traffic in the year of completion of construction. Completion of construction is A, which is equal to 3000 commercial vehicles per day. CVPD means, it is given, commercial vehicles per day, CVPD. As per IRC 37, the design traffic in terms of cumulative number of standard axles. The question is, what is NS? What is NS? And you have to remember this formula, 365A 1 plus R whole power n minus 1 by R into vehicle damage factor multiplied by lane distribution factor. And substitute everything. A is 3000, R is 6%. Remember here, while substituting R, if you don't have practice, in place of R, you are going to substitute 6. 1 plus 6 whole power n. That is going to become wrong. So R means it is fraction value 0.06 and VDF and other parameters, and you will get it in 10 power 6 standard axles. In 10 power 6 standard axles. So 10 power 6 means million standard axles, MSA. Next one, the radius of relative stiffness. Radius of relative stiffness means L. Radius of relative stiffness of the rigid pavements P and Q are denoted by LP, LQ. LP, LQ are the radius of gyration of the two pavements. The geometric and material properties of the concrete slab and underlying soil are given below. So for pavement P, the slab length is L, width B, thickness is H, modulus velocity E, Poisson's ratio mu, and it is K. For slab P, pavement P, length is same, breadth is same, but thickness is reduced to 0.5. Thickness is 0.5 H. Modulus of velocity also same Poisson's ratio, but soil subgrade reaction below soil, it is having 2K, soil subgrade 2K. The question is the ratio of LP by LQ is. What is L? You have to remember that particular equation. What is L? EH cubed by K into 1 minus mu square whole to the power of 1 by 4. So you need to remember that particular equation. E cubed by EH cubed by 12K into 1 minus mu square whole to the power of 1 by 4. So if you remember this equation and compare the various pavements P and Q, all other parameters are same except the thickness and the K values. Everything is the same and it is asked to find the ratio. It is asked to find the ratio. So only the two parameters are changed, remaining are same. So that means this is the original equation and L, radius of relative stiffness, is proportional to H cubed by K. H cubed by K whole to the power of 1 by 4. So LP by LQ is equal to HP by HQ whole cube, then KQ by K whole to the power of 1 by 4, and appropriately substitute the values given in the previous, the ratio will becomes equal to 2. So to answer this, you need to remember this radius of relative stiffness, this particular formula. Then it's a theoretical question, you can look at easily, you can understood. Then a traffic survey conducted on a road yields the average daily traffic count of 5,000 vehicles. Average daily traffic 5,000 vehicles. The axial load distribution on the same road is given in the following. Axial load 18 tons, 14 tons, like that 6 tons. And frequency of the traffic. So 10% of the vehicles are 18 tons axial load. 20% is with the 6 ton axial load. The design period is 15 years. The yearly traffic growth is 7.5. Lane safety factor 1.3. If the vehicle damage factor is calculated from the above data, VDF is not known. Above data. The design traffic means ultimate question is what is NS. So in the NS, vehicle damage factor is to be computed basing on this. It's a big question normally. It may be split sometimes in the two questions. What is VDF is a question and what is NS is a question. So what is VDF? First find out this is entire data given. What is VDF value? The standard wheel is 80 kilonewtons or 816 or otherwise 8.2. You can consider any of this. So VDF is nothing but already given. It is a sigma Fi Wi by W standard divided by sigma F whole power 4. It is given earlier in the theory also. So what you do, there are different class of vehicles. How many class of vehicles are there? How many class of vehicles are there? So here W1 by W standard, one is 18 tons then 14 tons, 10 tons, 8 tons, 6 tons. So here you can look at 18, 14, 10, 8, 6. These are the actual loads that are passing, and the standard load is 8.2 tons. And basing on this substitution, you will get vehicle damage factor as 4.989. Sometimes this may be the question in the examination. So just computing this. And once you got this VDF value and the design data NS value equal to when vehicle damage factor plus lane safety factor and substitute all the values, you will get 309.1 million standard axles. So this is how the various numerical problems in pavement design, and few more problems are there in it. Tomorrow I'll spend a few minutes on the various problems that are pending in pavement design chapter, and once it is over, then we'll switch over to pavement materials. We are going to discuss tomorrow pavement materials. So I am closing the session now. Thank you very much.